second video to going over the solutions for the second part of the April break notes that you're working on circuits. This video will actually have sound. I realized the last video I recorded doesn't have sound. Hopefully you can hear me now. Alright, so the four objectives that we had for the circuits unit, circuit section, is to be able to recognize common components of electrical circuits, to be able to explain and use Kirchhoff's rules to analyze branches in circuits, and to be able to explain the difference between series and parallel circuits and determine the voltage, current, and the equivalent resistance and power for both series and parallel circuits. Finally, the larger objective, and this is going to be the stuff that you guys are probably going to get assessed on the AP exam, is can you combine the techniques that you're going to learn in circuits 3 for series circuits with those for parallel circuits to analyze complicated circuits that have sections that are in series and sections that are also in parallel. So the first section I think that actually has questions is number 3, but I'll go over 1 and 2 really quickly. For circuit components, these are the basic components of circuit. Components are just things that exist in a circuit that do something. These are the examples of components. This is the symbol. The symbol is how it would look in a circuit diagram, which you'll see plenty of. Picture is a real-world representation of that object, and here's a little description of what those objects do. Things that you guys are going to see a lot of are wires, junctions, batteries, resistors. Lights, you're going to see when we get back in the review. Lights are basically resistors. They have the amount of current that runs through the light is going to dictate the brightness of the light itself. And that's something you'll learn about. We won't see too many switches, but switches basically close or open a branch of the circuit. Voltmeter, ammeter, and ohmmeters are all ways of measuring different, the voltage, the current, and the resistance. And the ground is the same as the ground that mentioned in the unit on electrostatics. Okay. So one thing to keep in mind with the battery is that the battery has two sides. It has a positive terminal and a negative terminal. The positive terminal here is going to be the one then the
opposite side. So the wider side is going to be the positive terminal, and the smaller side is going to be the negative terminal. Now, just like we talked about before, what's really important to note is that the direction of the current is going to be going from the positive terminal to the negative terminal. The current's going to be going like this, but the electrons are the things that are actually moving in the circuit, and so the electrons are going to be moving in the direction opposite of the direction of the current. Alright, so here's some rules. Here's some rules that a German guy named Gustav Kirchhoff came up with. He came up with the junction rule, which is the first rule that says, as a result of conservation of charge or conservation of energy, conservation laws in general, all of the current that flows into one junction, you can see it over here, these are how we represent junctions. All of the current that flows into a junction must be conserved, or all the current that goes into the junction must split apart into two segments of current that when they rejoin together must be equal to the original current. So if current I1 goes into junction 1 and then splits because there's now two branches of the circuit, current 2 and current 3, or current 2 and current 3 together must add to be equal to I1. Now, you don't know necessarily if they split in half. That's a common misconception. They might not necessarily split in half. It really depends on the resistance in either branch of the circuit. In general, a good principle, and you might have already heard this before, is that current likes to take the path of least resistance. And so, in general, you will have current that is higher where there's less resistance. It's simple physics. And we'll see how that is justified with Ohm's law in the next section. Okay. Also, definitely watch these video links at the bottom. Bozeman Science does a great job, and
it is always good to get a second opinion on, or a second overview of all the things that you're learning through the notes. We just talked about Kirchhoff's junction rule, and now we're going to talk about Kirchhoff's loop rule. Kirchhoff's loop rule states that all the voltages around a closed loop must add to 0. So basically, if you come back to any point in a circuit after going through the circuit, after the current goes through the circuit once, that voltage has to be the same, or that electrical potential has to be the same as it was before. Like every point in the circuit has to continue to have the same electrical potential, that no matter how many times the current goes through the loop. On to series and parallel circuits. You guys can read through the examples on different types of circuits. I'm really going to just jump to the questions. So make sure that you've definitely read over the notes and practiced completing the questions before you watch this video. Definitely look at the toll booth analogy. It's a very, very helpful way of understanding the idea of equivalent resistance. So read through this, use these pictures. It's good stuff. Be spicy. Alright. Now, for the check-in questions over here, we have diagram A and diagram B. Now, we want to identify whether these are series or parallel connections. And so, when I look at diagram A, I see that, okay, so the current goes from this part of the battery to here. Then, okay, so there's some funky stuff going on here. There's a voltmeter, there's a light, there's a speaker. Oh my gosh, I'm so confused. I've never seen this many different things in a circuit before. But it's okay, because all you need to know is that the current's going to split apart at this junction into 3 different branches, then rejoin and come back in here. So if it splits apart into 3 distinct branches, then you know that these are parallel connections. The voltage drop, or the voltage here, and the voltage here, the change in voltage must be the same throughout all of these branches, and that branch, that branch, and that branch, because the voltage here and the voltage here don't change. And so the difference between the two has to consistently be delta V, and so the voltage drop across these 3 branches will be equal. Now, in diagram B, you have the speaker, another resistor, and a light bulb, but they're all part of the same branch. So that means that this is in series. Now, we have 2 circuits, diagram below here for diagram A and diagram B. Now, we want to see which of the 2 devices are connected in series and which 2 devices are connected in parallel. So there's some really funky stuff happening now. For diagram A, you have an ammeter, or the current goes from this positive end of the terminal, encounters an ammeter and then a resistor, and then it splits apart to encounter a bulb and then a speaker, and then rejoins and goes back into the battery. So the things that are in series have to be the ammeter and the resistor, because those are the only 2 things where the current travels in the same branch. Over here, the current splits up into 2 different branches, and so that means that the bulb and the speaker are in parallel. So in series are the ammeter and resistor, and in parallel are the bulb and the speaker. In diagram B, according to some similar logic, we can see that the speaker and the ammeter are in series, and the bulb and the resistor are in parallel. Going through these will be helpful to see a more broken down process for analyzing circuits in series. I'm going to give you I'll go over these when we actually approach the problems. So something that you'll notice when you look at the example problem is that there's a nice little table that we're going to be using to analyze circuits. And so this table is going to be really helpful for you to use whenever you encounter circuit problems. So
You won't be given a table, but it's helpful to make a table that looks like this with the resistors, or the different circuit elements, in columns, and then the voltage, current, resistance, and power in rows. We'll see why this is useful, because there's a lot of different information that we have to keep track of here, and so it is very useful to have a table that helps us do this. Now, we have, for problem number 1, we have a battery that's supplying 14 volts of electrical potential through a circuit with 3 different resistors. And so the first thing I say is, okay, I'm looking at this resistor, or this series, the circuit, and I notice that the 3 resistors are in series. And so the first thing I want to do is find the total resistance. Let's put these on a sticky note. What are the things that we're always going to be doing when we analyze circuits? We are going to be doing this. First, we're going to be, and you should refer back to this, as like the Didai criteria. We're going to be finding for series circuits. For circuits that have components that are in series, we want to find the total resistance, find the current, using Ohm's law, find individual voltage drops, and then use the power equation, P is equal to VI, to fill in the column or the row for power. So, what am I saying? Basically, you have a circuit. You want to find how much resistance the circuit itself is providing to, or how much the resistance in total all of the components of the circuit are providing to the circuit. When you find the total amount of resistance, and you know the total amount of voltage, you can find the total amount of current that is going through the circuit using Ohm's law, V is equal to IR. So the first step helps you find step number 2. Now, once you found the total current throughout the entire circuit, you know that you can use Ohm's law to find the individual voltage drops, because you know there's 14 volts here, but the 14 volts are going to drop. Those 14 volts are going to be lost at each of these resistors, depending on how much resistance each of these resistors offers. And so, using Ohm's law, we can figure out, okay, so R3 has a fixed, all 3 of these resistors encounter the same amount of current, but they each have a different resistance. And so, according to V is equal to IR, they must have different V's, different voltage drops. And we'll go through an example here. Once you find the individual voltage drops, then the rest of it is light work, because all you need is the formula for power, VI, easy money. Alright, let me step over here. Alrighty. Alright, so when we approach this problem, we want to find the total resistance first. And so we can see that there are 3 different resistors here. All we have to do is add them together. And so when you add the 3 resistors, we got 33, 15, and 7.8. When we add those 3 resistors, we get 55.8. So total resistance is equal to R1 plus R2 plus R3, which is equal to 7.8 ohms plus 15 ohms plus 33 ohms, which gives us 55.8. Now, once we found the total resistance, we want to find the current. So we start off with V is equal to IR. We know what the total resistance is throughout the entire circuit from our answer to part 1. We know what the voltage is supplied by this battery. So we want to solve for the I. So the voltage is 14 supplied by the battery, and the resistance is 55.8 offered by the circuit. So when we divide those two, we get 0.25 amps. Now, the nice thing about finding the current is that the current has to be the same throughout the entire circuit because there are no loops or branches, or there are no branches, so the current doesn't ever split up, and so from here all the way around the current has to be the same. And so the current's the same. Note, this is only for circuits in series. So if the current's the same, then we can find the voltage pretty easily because we just go up the row, boom, 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 with V is equal to IR. And so all we have to do for each of these is multiply the current times the resistance to figure out the voltage. So for each of them, when we do that, we get 1.95 volts. That's 0.25 times 7.8. 0.25 times 15 is 3.75. And then 0.25 times 33 is 0.25. This is just V is equal to IR, and then an example would be for V1 is equal to I, which is 0.25 times the resistance, so 7.8. And that gives us 1.95 volts. Power is pretty similar. P is equal to VI. So all we're doing is we're multiplying the voltage times the current. So for each of these, for R1, R2, and R3, we just have to multiply the voltage at R1 and the current at R1. The voltage drop across R1 and the current that goes through R1. So multiplying these two numbers right here gives us, here, gotta grab my calculator. We have 0.49 watts, 3.75 times 0.25, 0.94 watts, and voltage times current right here would be and so we also know the total power dissipated throughout this 2.06. 2.1 actually, for consistency. 2.1 watts. And so the total amount of power that's dissipated is just the sum of all of the different circuit elements. So 2.1 plus 4.9. 2.1 plus 4.9. Oh my gosh. Plus 0.49. 0.49 plus 0.94. So that gives us a total power use of 3.53 watts. So that's one example. Now I'm going to do the next one in the same exact way. So here the resistances are given to you again. We have to find the total resistance here. It's just two more resistors, so we go through the same process but for two additional resistors. Now there's also two batteries, but that's fine because all the batteries are going to do is just add more voltage. So to find the total voltage here, we just have to add together the two batteries. So if there's 6 volts here and 9 volts here, the total voltage supplied to the circuit is going to be 15 volts. And so from here, let's see, the current travels this way and then the current goes this way.
And so the total is 15 volts throughout all 4 resistors. Now, we want to find the equivalent resistance first by adding the resistance of each of these resistors contributes. So we have total resistance first. Equivalent resistance is equal to R1 plus R2 plus 3 plus R4. No, it's just one more resistor, not 2 more resistors. And so when we add these, we have 10 ohms plus 22 ohms plus 68 ohms plus 4.7 ohms. We end up with 104.7 ohms. So that's the total resistance throughout the circuit.
Now, once we found the total resistance throughout the circuit, we can then find the current. So, V is equal to IR. We have the total voltage. We have the resistance that we figured out. We have to solve for I. And so we end up with a voltage, or we end up with a current of 0.14A. 14 amps. And so you have 0.14 amps exiting this battery, and we know that because this is all one branch, that current is going to be the same throughout. It's just like the last one. Now, V is equal to IR. Same stuff again. Just multiply the current times the resistance for each of the resistors to find the voltage drop. So for VI, for R1, the voltage drop is 0.14 times 10, which is 1.4. Volts, 0.5 volts, 0.66 volts. And for the power, it's the same thing, or the same idea. Power is equal to V times I, the voltage times current. So for each of these. And so for these, let me use my phone calculator. It's a little easier for me to use. Right. We got our calculator app. So then for each of these, we will multiply the voltage times the current. So the first one's 1.4 times 0.14. Oh, that's funny. 0.196 watts. So 3.1 times, next line is 3.1 times 0.14. Yeah, you can totally skip over this part of me just plugging numbers into my calculator if you've already done it. In fact, I always encourage you to skip around through the videos if there's one part that you feel like you already know. But I'm sure you do that anyway. We go through here, and we just add all of them together. That is how you complete an analysis for two circuits in series. Now, what if they're in parallel? Things become a little more tricky. Parallel, the current is going to come out of the battery and then split up into different branches. You can see here how in this figure it's drawn in where the current splits. And that's going to be at each junction. And so at each junction the current's going to split into two paths. And once it splits in one path, then that path might encounter another split, right? And so depending on the pattern of splits or depending on the pattern of junctions, you might have different parts of the circuit being in parallel versus in series. And so for this circuit, this example, all of these resistors are in parallel. So at each, we already went over Kirchhoff's loop rule, junction rule, and another really helpful tool is to recognize that the voltage drop across all these three resistors in parallel must be the same. So the voltage at each of these points is going to be the same. The voltage at each of these points is going to be the same. This is the initial voltage, and this is the final voltage. From each point on this side of the circuit to that side of the circuit, delta V has to be the same because the final voltage on this side of the circuit is the same as the initial, or is the same. Doesn't matter whether or not it's at this junction, that junction, or that junction. It's all on one side of the circuit, then the final voltage is the same. And so the change in voltage will all be the same across all of these three resistors. And so V1, or yeah, V1, V2, V3 will be all equal. And then the power is just based off of the current and the resistance. Now, when you have a circuit that is in parallel, with resistors in parallel, there's going to be a slightly different rule to find the total resistance. Instead of doing Req, or R total, is equal to R1 plus R2 plus R3, you can't do that for parallel circuits. For parallel circuits, we have to use this weird old formula with 1 over the R total, or the Req, is equal to 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3, and so on and so forth. Now, the analogy that we used before for water, or for current and water and how they're related, is really helpful when we think about equivalent resistance, or the total resistance, when there are multiple channels or the multiple paths for the water to go through. So if you have a set of pipes, it's going to be a lot easier for the water to flow through that set of pipes than it would be for the water to flow through one pipe by itself. This is very, very similar to the toll booth analogy. The more paths you create for water or current to travel, the less resistance there's going to be for the current as it goes through the circuit. And so you can see mathematically, the more resistors you add, the more paths you have for the current to flow through, and the bigger, or the more you're adding on the denominator, the smaller the overall numbers you may have to get. Okay. And so the process that we have for figuring out analyzing parallel circuits is kind of similar to the process for series, but also different, and we'll talk about why. So when I see a circuit like this, and I notice that, first off, if you ever see anything in kilo ohms, change that to ohms immediately. It's just telling you that there's a lot of resistance there, but make sure that you rewrite it in terms of ohms so that all of your units are consistent. Now, we want to do the same thing we did for the parallels, or for the series circuits that we're going to do now for the parallel circuits. And so the first thing you want to do is take a look at the circuit and see, okay, so which sections are in parallel and series? This entire circuit is in parallel because the current's going to go through here, split into these two branches, come back, and there's nothing else that happens. And so once you recognize that, you are going to determine the voltage drops across each of these resistors. Determine voltage drops. You're going to use those voltage drops across each of these resistors to find the current. So using Ohm's law, you're going to be able to find the current across each of these two junctions. Once you find the current, then the reason why we're not finding the equivalent resistance first is because we have another option besides using that really funky formula. We can actually find the individual currents through both of these branches, and then add those individual currents to find the total current. This saves us a little bit of time and allows us to not do that funky math with the equation. And we will need to use that equation for later circuits, but for these we won't need to. Now, find total current. Find total resistance. And then finally, we use the power formula. Alright, so let's follow those 5 steps for this table right over here. Okay, for this table, we know that the voltage drops across this resistor and that resistor have to be the same. So whatever the one voltage drop is, the other one is going to be the same thing. So let's use So if there's 24 volts of electrical potential on this side, there has to be a drop of 24 volts on this side as well. So for both of these, the voltage drop is the same. Now to find current, we have to do V is equal to IR. So we know V, we know R, so we have to find I. I is equal to V over R. So the voltage drop is 24. The resistance is 2,200 ohms. This is I1, 2. We end up with 24 divided by 24 divided by 2. For this section right here, we end up with 0.01 amps, and for this section, we end up with 0.005 amps. And so you can see clearly that the more resistance there is in that branch, the less current's going to flow through it. Current's going to want to take the path of least resistance. And so when they rejoin, once it splits up into two separate currents, then we know that when they join up, they're going to have to combine. And so the total current is going to be 0.015. And now with the total voltage and the total current, we can find the equivalent resistance because we have Ohm's law. So we found the total current, find total resistance. So V is equal to IR. Again, we know that the current is 0.0, R, we have to solve for R. We have current and we have voltage. R is going to be equal to V over I. And so we have the voltage of 24 divided by the total current, which is 0.015. So we end up with 1,600 ohms of resistance. And this makes sense because the total resistance is going to be less than each of the individual resistors. Remember, the resistance will go down. The total resistance for a circuit will go down as more resistors or more paths for that circuit to travel around are added. So adding more resistors would decrease the total resistance. Power we do in the same way with that formula. P is equal to V times I. So voltage times current for each. Voltage, current, voltage, current. And so when we do that, we'll see 24. We get 0.24 watts. Watts, and then the total is just the sum of the two wattages there. Now, fill in the table for the following circuit. Going to do the same thing, but we notice here that the current goes through into this junction, splits into three separate junctions, or three separate branches. So this one's a little bit funky. So the total voltage drop across all three of these resistors is the same. So we're going to go and do this step first. 24V, 24V. Now we're going to repeat the process again for the current to find the current across each of these resistors. So V is equal to IR turns into I is equal to V over R. So we have I1, resistor 1, I2 is equal to resistor 2, I3 is equal to V over resistor 3. So the voltage drop is the same. The resistor 1 is 1. Voltage drop is 24. Resistor 2 is 2. So I'll say that there's 24 amps going through that one branch, 12 amps going through the other branch, and then 8 amps going through.
And so the total current has to be the sum of each of those currents together, and so the sum of all the currents combined. So we have 24 plus 12, which is 36, plus 8 is 44. So there's a total of 44 amps of current running through the circuit. Now with the total voltage that we have and the total current, we can find the resistance.
So then
R
R,
is equal to V over I, and we end up with the voltage here, 24 divided by the current, 44. And we get something like 0.55 ohms. More resistors you add, the smaller that overall resistance is going to be. And then finally, we have to use the power formula. P is equal to V for each of these. So you multiply voltage times the current. This is 576 watts. Wow, that's a lot of watts. That's 288 watts. And this is 24 times 192 watts. So the total power dissipated by the circuit is just the sum of these. Or approximately 1 kilowatt. Final one for number 3. Okay. This is funky because when we look at this circuit and we see the current flows out of this battery right over here into the 4 resistors that are here, but like at this point it branches, and then here it branches, and then here it goes down, here it branches, and here it branches, and this point goes down. And so all of these sections are in parallel with one another. So to find the total resistance, we just have to approach this problem in the same exact way we approached the previous problems. So we know the voltage drop across everything, the voltage drop across this entire segment of resistors, it has to be the exact same. It's 4 volts here, 4 volts here. If we found determine the voltage drops, then we have to determine the current using V is equal to IR. So V is equal to IR. So this one will kind of speed through a little bit. So the current is going to be the voltage divided by the resistance. And then one thing to keep in mind here is that these resistances are in kilo ohms. So make sure that you rewrite these into regular ohms so that we're being consistent with our units when we're solving for amps. Alright, so we have 4 divided by 1000, we get 0.004 amps. 4 divided by 2200, which is 0.002 amps. 4 divided by 6800, which is 5.8 times 10 to the negative 4 amps. And then we have 4 divided by 470.6. So 0.0085 amps. So the current is going to be, the total current is going to be the sum of all of these little numbers. So you'll end up with 0.004 plus 0.002 plus 0.0005. Plus 0.0085.
So we get a total current of around 0.15 amps. Now, V is equal to IR. We can find the total resistance with dividing this total voltage drop by the total current drop, or total current. So 4 divided by 0.15, oops, 0.15. It's going to be equal to 26.7 ohms. So by different paths for the current to travel by, we've really dropped the overall resistance of the circuit. And then finally, for the power, we do the same thing. P is equal to V times I, so we're multiplying these two numbers. Okay? 4 times 0.004. 4 times 0.002. 4 times 5.8 e to the negative 4. And 4 times 0.0085. And we add each of these 4. And we have, voila, power. Okay. I'm going to send the breakdown for the complex circuit analysis in another video because this video is already 40 minutes. Make sure that you follow along with each of the problems, you are cool with the solutions, watch over the sections where I went over how to do each of the problems if you don't get it the first time, and make sure that you have this completed by the start of class on Monday. Alright, I'll be sending another video. Adios for now.